In this video, I want to have a look at simple harmonic motion, so what it is and its key features. So a particle is in simple harmonic motion if it oscillates about an equilibrium point. So two words in there that are important. Oscillates means it moves back and forth in a regular rhythm in a straight line, and about the equilibrium point means there's a central point that it's moving back and forth about, and it's moving an equal distance on either side of that equilibrium point. So some examples of things that move in simple harmonic motion might be a pendulum or a person on a swing. So they're moving left to right or front to back. We can also think about a buoy that's floating with the tide, or a weight that's attached to a spring, so that's moving up and down along a straight line. Or we can think about a plucked guitar string and how it moves as well. Now obviously in real life there's something called damping which slows these down. So that might be something like air resistance, for example. That means that there's other forces acting on this motion that change the way it's moving over time, and it slows down and eventually it'll stop unless there's some other force keeping it going. For now, we're going to completely ignore that and pretend it doesn't exist, and pretend that if somebody's moving on a swing or if your pendulum's swinging, it's just going to keep going in that simple harmonic motion indefinitely. Alright, so I want to specifically think about somebody swinging on a swing. Everyone's been there, so I want you to think about what that motion is and how the velocity and acceleration are changing when you're on a swing. So we're going to go through and have a look at the key features of simple harmonic motion with that example in mind. So if we think about displacement first, displacement is zero at the equilibrium point. So if you're swinging on a swing, that'd be at the bottom of the swing. And it swings regularly between its two endpoints. So if you're on a swing, you're swinging up and back, and you're going equally far forward as you are coming back. And we're just going to swing regularly between those 2 points. Those endpoints are the maximum distances that it reaches from the equilibrium point. If we look at velocity, if a particle or an object is moving in simple harmonic motion, the particle has its greatest speed at that equilibrium point. So again, if you imagine swinging on a swing, then you are going your fastest as you hit the bottom of that swing. So as you're coming down, you're speeding up, then you're going your fastest, and as you start to come up the other side, that's when you're slowing back down again. So it's momentarily at rest at the end points. So when you get to the top of your swing, you momentarily stop before you turn around and travel back down towards the equilibrium point. So for our object in simple harmonic motion, the acceleration is going to be the greatest at the end points, so when you're at the top of your swings. And it's always going to be in the opposite direction to the displacement, and that's what makes us turn around. The acceleration is always directed towards the equilibrium point. So if you're swinging backwards on a swing, the acceleration is acting on you in the opposite direction. If you're swinging forwards, the acceleration is acting in the opposite direction. And again, that's what makes you turn around and head back towards that equilibrium point. Acceleration is zero at the equilibrium point, and then it's going to change its direction. So as you're coming down the swing back towards the center, the velocity and the acceleration are both working together and you're speeding up. Once we hit the bottom of our swing, that equilibrium point, acceleration changes direction. And so we're moving up away from our equilibrium point. So our velocity is still moving one direction, but our acceleration is working against us then. And again, that's what makes us turn around. So just to say that again, as the particle moves towards the center, the velocity and acceleration are working together. So our particle is speeding up. As the particle moves away from the equilibrium point, velocity and acceleration are working against each other, and so we're slowing down. So we've got two really important points from there. One is that the displacement and the acceleration are always the opposite signs. So if your displacement is positive, then your acceleration will be negative, and vice versa. If your displacement is negative, your acceleration will be positive. The other important point is that the magnitude, so the size of our acceleration, not ignoring direction, just the magnitude of it, is always going to be proportional to the distance from the equilibrium point. So how far you are from that equilibrium point determines what our acceleration is. So keeping that in mind, we come up with this formula, that our acceleration is always proportional to our displacement. So n is just a number, it's going to be a constant. The reason we have the n squared there is to make sure that that becomes positive, and then we can put the negative in front of it, so that our displacement is always going to be the opposite sign to what our acceleration is always going to be the opposite sign to our displacement. The other formula that's given to us on our formula sheet is that the displacement of a particle is given by x equals a cos nt plus alpha. So that is going to have an amplitude of a, whatever that number out the front is, and the period is going to be 2 pi divided by n. So this is the equation that's going to describe the displacement of our particle, and we can prove that this satisfies this equation here. So we can rewrite our formula or our equation for displacement, that we've got x equals a cos nt plus alpha. Now if we want to differentiate that to get velocity, we know that cos differentiates to minus sine, and that we're going to have to multiply by that derivative of the inside, which is our n. So we'd have minus n a sine nt plus alpha. Now if we differentiate again to get our acceleration, we know that sine differentiates to cos, and again we're going to have to multiply by the derivative of the inside, which is that n. So we'd end up with minus n squared a cos nt plus alpha. But this whole section here is what we started with, so we can just replace that with minus n squared x. All right, so that's an introduction to simple harmonic motion.